as Zuhair mentioned, I am one of the Android engineers here at KeepSafe, and today I'm going to be walking you guys through sort of how we went from an app that had absolutely no encryption to an app that's fully encrypted, and how we went from, or how we didn't degrade the user experience at all by doing that. Because typically when you think encryption, you're like, oh, our disk speeds are going to crap, totally crap, right? So basically with encryption, you have a few goals, or at least we had a few goals. The main goal, of course, which is a very obvious one, is security, right? So we have people importing their private photos and their very important documents into KeepSafe so that no one else can see them. And if anyone could just go to our KeepSafe folder and then look at the files directly by changing the file extension, then that's a problem, right? The other thing is speed. So currently, without encryption, you just have the base disk speed. When you add encryption, you're always going to slow it down. Slowing it down depends on how you implement the encryption and how badly optimized the encryption is, right? And the last few things are ease of use for the developer, the end developer. It has to be very easy to use. Otherwise, no developer is going to care or implement it properly, right? And it has to be fail-safe. So all operations within encryption have to be atomic. They either all succeed or all fail. You don't want partially decrypted or partially encrypted data at all. And the final thing, which is don't degrade the user experience at all. So to begin, as I said previously, KeepSafe before, like years ago, had no encryption. And we basically relied on a hidden folder, which will fool your grandma, but won't fool like the 14-year-old kid who's semi into tech, right? So at first we didn't think this was a big deal, but we sort of started Googling, like, you know, how to hack KeepSafe. And suddenly there's videos that pop up, and like, you have some kid talking to a microphone. He's like, so this is how you do it. You copy all the KeepSafe folder over, you change the file extensions, and here you go. And we're like, all right, that's pretty crappy. And then we started getting reviews where people are like, you know, I just saw my pictures by going to the, you know, the hidden folder. And so we're like, all right, we need to fix this. So basically our cleverness was wearing off because that was just a clever trick. So our first thought was, okay, we can avoid encryption because to us, when we said encryption, we're like, oh great, the app's gonna be slow now. We can avoid encryption by, you know, doing some sort of obfuscation or some sort of clever trick to randomize the data or randomize the order where the data is read. But we quickly realized that it's not very effective. So here was one of the ideas where we're like, okay, we have files. We'll encrypt the first few bytes and the few last bytes. The idea was like, that'll generally make everything unreadable to a standard parser, and it's still quite fast, right? However, you don't want to do that because it's very easily broken, right? There are a few reasons. It's not actual encryption, it's just a clever trick again. And it's prone to outliers. So basically, every phone now will save a photo and it'll be at least 3 megabytes. If you encrypt just about 1,000 bytes, you're not really encrypting much. And it's very easy to figure out. If anyone imports a photo, they can diff it against the original and see that we only changed a few things. So that's when we move into actual security. Basically gunned down and said, all right, we need actual security. And so when looking through encryption, you have several options. And what we went with was the advanced encryption standard, which is currently the most used encryption method in the world. And there are no known successful attacks, or, well, I can't say that because there's been successful attacks on certain modes of AES. But it's been approved by the government to hide top secret documents with the largest key size, which is 256 bits. But the most important thing is that it's not a cheap trick, and that's what we want. So just to give everyone a little basic introduction, whether you know or not, AES uses block sizes of 128 bits, which is 16 bytes, has 3 different approved key lengths. Typically 128 is used. We use 256. It's a symmetric algorithm, meaning the same algorithm is used for decryption and encryption. And it's a symmetric algorithm because it uses something called a substitution permutation network, which basically means the way it shuffles the data around is reversible and all sorts of things like that. And yeah, it's been approved by the National Institute of Standards and Technology. So it seems like a good pick. So now that we had that out of the way, we have to figure out how to put it into KeepSafe. And we also have to figure out how to store user data, because all we have now is a folder of pictures that are still in plain text. And we need to transition that into a folder of encryption pictures, right? But the most important thing, again, is that it has to be fast. Because if you use our app suddenly and everything is just way slower, you're going to uninstall it. You're not going to be very happy. So we'll tackle the storage problem first. Basically, you have two options. You'll have either an archive format, which is basically a zip file, or some other form of archive. Or you can just keep them separate and have them all encrypted separately. If you have an archive, you have to deal with peculiarities with the file format and seeking time. If you keep them separate, you have them all nicely ordered and you don't have to deal with an archive format. But you have to add a slight overhead per file to store an additional data to help decrypt the file, right? Overall, we tried both options. The archive format just was much slower than having each file individually encrypted. So we went with that. So when you have separate files, that means you can't just decrypt one thing, have the app live, and then at the end re-encrypt it and then re-encrypt it and say that's it. When you have separate files, you have to decrypt each one as they come into use, which means that the encryption has to live and not be a static thing, which means we need to implement an on-the-fly decryption mechanism. So for that to be possible, AES works with block size of 16 bytes, and it assumes that you're just doing it in a static manner. However, there are certain modes of AES that allow you to transform the block stream into a stream cipher, where you can work on it as if it's coming from a stream, where you're somehow downloading it or something like that. One of those modes is CTR, which stands for counter mode. And when we have AES in a stream cipher using counter mode, it introduces a new bit of data called the IV, which is the initialization vector, which is essentially a size 16 bytes, which is the same size as a block. And typically, it's just XORed with whatever plain text you have, and then modified for each successive block. So now that we have this, we have the counter mode, and we have a stream cipher, we can easily implement an input stream or an output stream that we could just put into Java and then write our stuff out. So with that, we implemented 3 classes: encrypted input stream, output stream, and random access input stream. It turns out that with a little bit of math, you can make it random access and have pretty good results. So typically, with this, you would have to, if you want to say go to this position or 50% into the file, you'd have to decrypt the entire first half, right? But with CTR mode, you're able to pre-calculate the IV value of the position you want to go to, so you can just skip the first half and go directly to where you want and decrypt whatever's there, completely eliminating the whole slowdown of decrypting the whole file first. The problems of this are seeking and chaining data. So seeking is simply math, where you go to the position, divide by the block size, and you, with integer math, you have the block position, and that's where you start decrypting. And also for the IV, you would increment it by that same amount, and then your plain text would come through. The other problem is chaining data, which is where, depending on where you start, you might go over multiple blocks with your read request. So you need to figure out that you are going over multiple blocks and that you need to chain the data together. Because again, this only works per block. So we did that. We solved those problems pretty easily with just a little bit of math. It's not too complicated. But it was worth using Java Crypto, which we figured out quickly was really slow. So that put us at a little odd position because we were so happy that we figured out we could do all this, and we get to the very end, and the app's slow. So then we started looking around, and we thought that, you know, we could just put in a C library or something native and just make it a lot faster. And so that's where the JNI comes in, which is the Java native interface. Hopefully none of you guys had to deal with that. Basically, this allows us to bring in any crypto library that was written in C, C++, and just shove it into the app, and then call down to that library instead of Java when we need to do our crypto. So we went shopping. So when you look for a cryptography library, the things you want to look for: ease of use, whether it's open source or not, the certification and its maturity. So when I was looking around, I found one called by Wei Dai called Crypto++. You guys may know Wei Dai because he wrote the article on B-Money, which is the main influence behind Bitcoin. But he wrote this library called Crypto++. It was fast. It pretty much beat all the other libraries and benchmarks. And it was small and compact, open source, and was certified by the government multiple times. And it's also 20 years old by now. So that's great. We have our library. And here we can go through all the little things to look for. So with Crypto++, you have 7 lines of code here, of which this could be made into 2 if we made that 1 line. But basically, you just declare a CTR mode object. You give it a key, you give it the IV, and it has this nice little paradigm where you have source, transformation, and filters in a sink. So you have a file source, you have a transformation, which is your encryption or decryption, and then you have a sink where all this stuff goes to. So in Crypto++, you have a source stream or a file and stream. You have transformation, which is the decryption. Then you have a sink, which could be a byte array or another file, which is very nice. It sort of abstracts all the weird, you have to use this certain key size or whatever. All you care about is that it's decryption, a key, here's your file, this is where I want it, and you're done. The other thing is it had to be open source because we wanted to know that we could trust the code, and if we ever had problems, we can go in and look at what's exactly going on. The good thing is it is open source, and the author does not distribute binaries at all. So you need to compile it yourself, which is an added bonus. And the other thing is certification. So it has FIPS certification 3 times, which is the Federal Information Processing Standard, which basically means the government looked at it and yes, this library knows what it's doing, this is proper cryptography and math. Which is good because you would hope that would be correct. And finally, maturity. The library started out in '95 and is about 19, 20 years old by now. And it's still actively developed because the last stable release was last year and there's a new one coming pretty soon. So that's always nice to see that the developer still cares about their project. So great. We have the method, the on-the-fly decryption. We have the library. We have it put together through JNI. So then we can call down to the C library from our code. And this is how it all works together. Where right now we have our input, which would go to the JNI, which would go to Crypto++, which would come back and give us our output. And we encapsulate all that through our encrypted input or output streams, which is an extension of a filter input stream or output stream. And the great thing is that this is fail-safe because we only do soft decryptions into memory. Whenever we encrypt something, we also make sure it's atomic, so that if we fail decrypting something, we never touch the file in the first place. If we fail encrypting something, we don't move in the original data, because we create a copy when we're moving in data. And so finally, we have a little code demo. So this is actual source code that'll work in KeepSafe. We have about 7 lines of code here where we easily just create a file output stream, and then we create an encrypted output stream which wraps the file output stream. And then we pass the encrypted output stream to any function that would normally take an output stream, and it'll just work. And that's great. The reason why we don't use a templated function or a templated class design is we don't know what sort of input stream you want to give us. And the nice thing about having a separate object for the file output stream is that we can call it and use something like getFileDescriptor.sync, which is a pretty important step when saving data on Android, as you may have seen in our previous talk. So that was writing a bitmap to disk, and this is reading an image, which is 3 lines. And it works just as you expect it. You pass it an input stream, Android looks at it, doesn't even know that it's being decrypted. It just is completely normal. Decrypts it, and you have your bitmap. And so when putting this all together, the last thing we needed to make sure was that, was it still fast or was it slow? And thankfully, as you can see, on the left side we have the encrypted data, and on the right side we have the unencrypted data. And I'll leave it up to you if you can discern the difference in the performance. So to me, I don't see any difference, and the users also haven't seen the difference because they have complained about it. So I would say that's a job well done, and we succeeded in our task. I didn't really choreograph these videos very well. But yeah, that is the story of how we put encryption into KeepSafe.